So, welcome back. This, I believe, is lecture 14 of Dynamics on Networks. And as always, I need to remind you that this is live streamed and recorded. And I'll do my best to edit the recordings and make them available. They're always available, but I'll do my best to edit them. It doesn't always happen instantaneously. We're going to continue today talking about Null Clines and then I hope start on two-dimensional stability. We had reviewed Null Clines very briefly last time, and today I want to dig in a little bit to the Null Clines, doing the exercise that we went through very quickly in the end of last class, and then doing a more interesting exercise on the Fitsu-Nagumo model. And so we're going to start out by just reviewing some of the main concepts from last week, and then we will talk about Null Clines, go over the basic workflow for Null Clines, because it's one of these things where you need to do a lot of practice, try a couple of simple examples, then work through the Fitsu-Nagumo equations, which I think are the first non-trivial example where Null Clines give you something quite meaningful. And then I hope we'll be able to do some of the higher order stability. My guess is we won't get through all of the stability analysis today, but I hope we could get through some of it. And I'd like to do quick project check-ins. It's okay to say you haven't done anything, but I would like to hear quickly where everybody is on their projects. In principle, you're supposed to have a project ready to present next week. I'll remind you of that. And so I want to find out where we are with getting that done. So maybe Elmar, we'll start with you. How's the project coming?
Yes, so I'm at the moment have not yet something to show, but I catched up over the Thanksgiving and start to implement the network. But I just really have done what they have in the paper. I have not really explored it, and nothing exciting to show because that it's just the network that I translated. Yeah.
Okay, one thing is, again, I encourage people in the class to talk to each other, even if you're not working together on projects. And I will ask people to review each other's projects after next week. One thing you could certainly do is go to each other. For example, if you're more or less familiar with some of the Colab issues or the IPy widgets issues. Some people have used them a lot, some less, and so it's worth talking to each other for ideas on that if there are issues. Alex, sorry, go ahead.
I have not yet actually used these widgets, but I have found one little command I can post it in that not makes visible when it have to load in the beginning all the libraries. And I think it's nice that that it not goes like this and then you have to click it away, that it's just that's it in the background. I can post this in the chat. Yeah.
By the way, Elmar, Herbert really liked your using that reset function to restart the kernel in Colab. He didn't know about it.
Nice. Yeah, and there I have now one line on top of that. Great. Yeah.
Even better. But they're going to change their recommendation for their documentation based on what you did.
Oh, cool.
So
okay.
You should send your update to them and make sure that they give you some byline somewhere thanking you for coming.
Oh, not because of such small things. But actually it was interesting because this plot function, not the plot array, the plot function seems really to be broken, and I think they because I pointed out they will re-implement this now. Hopefully, this was only one feature, but there are many features broken, so it looks like this is very old, and the plot array is really modern Python. So, but yeah.
Well,
nice.
You can always use matplotlib. You don't have to use their internal plot functions.
I try to learn the software, right? That's what I try to. Of course, I could always find a way around, but that's what I try now to do. Yeah.
But Lucian Smith is in charge of it. It's usually pretty responsive. So if you
tell him, I had the impression. It was a girl, I think I talked to. I don't know her name. I can't remember. Yeah.
I don't know. I mean, there are other people in the team. He has a big group, but great
Yeah.
thinking. William,
Yeah, so I have some questions. Maybe I don't know. Well, one for Colab. This is probably really dumb, but I don't know how to show an image. And I used, maybe I could just share. And I don't know if what the way I've done this makes sense, but I mean, I can also, could you stop screen sharing? Yeah, okay. Where? Okay, maybe here. Okay, so, all right. I gotta get rid of this. How do I get rid of this? Okay, so, biological background, I'm sort of like, I don't really know any, I don't know, I gotta write more or whatever. So I wanted to break down the math first, like the equations and write it out for people. But I mean, like, looking at the right side, like, I can't even read this. Like, it's so bad. Like, I don't know if it's bad, but it's so, it's hard to read. There's no, I don't know how to like break it up more. I'm open to suggestions. And I mean, my idea was to explain all this, what all this means. And I mean, this is obviously rough. And then that's the model and to show what this is and then explain this. I haven't finished. And then I'm going to start changing stuff, like changing the amount of DNA damage. But I mean, it's sort of hard to, I don't know. I guess that's interesting. I don't know. I don't know. I don't know. I'm
Can you
sort of
do
open.
shift enter? So now you did shift enter, right? So can you read it when you
What
when
do you
it's
mean?
full?
Like
Is
this?
this better? Yeah, is this better or no?
Yeah, I guess. I mean, I get, yeah, but I don't know. Maybe it's just me personally. I don't know. I don't really like it. Obviously, I think I'm gonna change it, but then like this image thing doesn't show up, so I don't know. I put the image over here, or no, where did I put it? I put it over here. Oh, it's gone. So I don't know how you can store. I don't know how to store files in the like.
You can not, as far as I know, you always have to upload it from scratch and Colab.
But then how did previous projects do it? Or were they on nanoHUB and it's different? I
And
don't
nanoHUB,
understand.
yeah.
so
Yeah.
Hayden, you've been working with a lot of Colab notebooks, so you might have some suggestions here. Because this is our first semester using Colab for the distribution, so I know how to do it on nanoHUB,
Well,
but
I
I know you could change
well, I
the
think.
sorry, go ahead.
Well, I was sorry. I mean, I was gonna say for the image, I did it by just giving it a source and then just the name of it. But you can do it by URL. I'm pretty sure. I think. I don't know.
Yeah, I'd have to take a closer look. I'm not entirely sure.
Okay. Because I think that's pretty important. I mean, I gotta
Well,
have
if
some
you have
images.
if you have everything stored in a Git repository, then you can pull the images from there.
Oh, okay.
So Colab
Okay.
will
Okay.
work with GitHub repository. And I
Okay.
haven't
Okay.
done that yet, so you'll have to figure that out. And if you want to document that, I'm sure people would be grateful. But
Okay.
maybe that's something where you guys could get together and have a discussion about that, because I think the concept is you should have a GitHub repository and then you reference materials that are sourced or stored.
Yeah, I think that's right. Okay. Okay, sounds good.
In principle, if it
Uh,
was in a Google Drive, you could also do it, but I think a GitHub repository is more stable than a Google Doc or Google Drive.
okay.
I think Hayden, you have some demo notebooks from David Umulis's classes, so maybe we could share some of those for people to look at.
Yeah, I can find a couple with some images embedded.
And I see, William, you've got the sliders working, so that's good.
Yeah, that was not that bad. I took it from one of the year previous students.
I mean, the other thing is that when you launch it, you want it to launch in basically a user mode rather than an editor mode.
Yeah, I know.
So
I don't know
the
how to
user
do that.
doesn't see the lines of code, and I don't know how to do that, but I would guess
I don't
that
think it's possible.
I'm sure it's possible.
I was looking at it. Let's see.
I know nanoHUB lets you do it.
Yeah,
But the switches won't be the same.
it
Does that,
says. I mean, I'm saying there is no presentation mode. That's just the first thing. I think that's.
Hayden, maybe that's something you can, maybe, again, maybe the group is, it's going to be something we all face. So if somebody can figure out how to launch it in a presentation mode or a user mode rather than an editor mode, that would be fine.
Okay, so I implemented all the equations in Tellurium. I noticed some mistakes and I corrected them until I got the same number of reactions parameters, double checked. Then I wrote all the parameters with the values they from their table, and it runs. So the syntax works. I mean, they are all named correctly. And this is the result. I had to use log scale in the y-axis because I couldn't see exactly what was going on, and I'm not sure if it's correct. So I started noticing some weird things. For example, they don't have anything the viral action. So they are using TNF alpha. So the level of TNF alpha plays the role of the viral acting over the cells. So they don't have like viral load or I don't know, viral RNA, stuff like that. They don't have it. And I plotted the interesting species, which are interferon alpha and beta in the environment, IRF 7, TNF alpha mRNA, and TNF alpha in the environment. And I find it weird because so this is in moles, and yeah, that's what I think. This is in moles because in the equations they divide the rate by the Avogadro number. So this is in moles, which means, for example, if you take interferon alpha, which goes to 10 to the minus 49, even if you multiply by the Avogadro number, it doesn't make sense. It's like, how can you have 10 to the minus 10 to the minus 20 molecules in your system? So, okay, it's 0. So then why do you have interferon alpha? Is it really responding to a viral infection? I'm not sure what's going on. So they don't have this specific graph because their graphs are done with the Nipah virus proteins interfering in the network. So they don't have like this result without proteins P, W, etc.
Well, so I guess one question is, why are you trying to replicate something if it doesn't make sense?
So in which sense it doesn't make sense?
Well,
I
you're
mean,
telling me that you're getting a plot that you don't think makes sense.
yeah.
And so you're asking a good question, which is what's wrong, which is reasonable. So you're telling me that these are equations that they've used in their simulations.
Yes.
And how have you changed it from what they did to what you're doing?
I just did not include the Nipah virus proteins.
So you're basically simulating an uninfected cell.
So this is, it's possible that this is what, yeah, so let me access let me access the, to make sure this is the case. Where are you? Supplemental materials here.
I mean, I wouldn't go through this here. It's okay. I think as a matter of principle, you don't want to start writing code until you understand what the model does. And so,
Yeah, the problem is in the equations, the proteins, they appear as a inhibition process.
okay.
So it doesn't seem like the proteins are promoting anything.
Well, so what does it mean if there's what does inhibition mean? It means that the product is produced if in the absence of something. So in the absence of something, those are turned on. So if I look at these equations here, you have an R1, an R2, and R3, which are all basal transcription rates.
I have those.
Right, so there is production. But
Yep.
again, I mean, I think the critical thing, and I know it's not easy when you start with somebody else's paper. That's why replication is difficult. Is that you really should be making sure you understand the circuit before you try to write equations for it, and then make sure that you believe the equations do in fact represent what you believe the circuit should do. It's okay to start out by replicating the code that they've written. But if it is hard to understand what the code does, then it's more of an issue. This is one of the reasons you try these exercises, because until you run into these problems, it's not so clear how to document your own code, how to do things, how to present the ideas that you're trying to present. But fundamentally, these are, as you point out, some of these, well, TNF alpha here is an activating Michaelis function. These mostly look like activating equations, actually, not inhibitory.
Yeah, I'm talking about the role of P, V, and W proteins. This IC
Yes.
inhibition coefficient
Mhm.
depends on P, V, and W. So yeah, if they are zero, I mean,
So
this,
two of those three are activating. Which two are activating?
let
No,
me
look
see
at
what
the equation. No, don't change there. Don't move. Leave it where it was. No, just look at the equation for the IC equation.
Oh, I got too far down.
You said that they were inhibitory, but in fact, two are activating. Which are the activating?
E and V, yeah.
Yes. So the only one that's inhibitory is W.
I gotta include everything here.
So
Okay.
you can actually estimate the behavior of these equations completely by hand without doing any computation.
Just setting different values of IC, this multiplier here.
No, that's right. I mean, this
Mhm.
is the maximum value of this is 1, the minimum is 0.
Yeah,
If
but
P,
this
if
is the
P,
problem.
yes,
Because in my case, I have it 1.
you have it always 1.
Yes.
Okay, that's fine. So that would be in the case where P is large, V is large, and W is 0. Yes. Yes.
Yes. Yeah, that's the case because I don't have anything multiplying these terms here,
Yes, okay.
but still I have like something that I don't understand.
What don't you understand?
Why is the concentration so low? I mean, is it so low? I could be crazy.
But you can evaluate that exactly analytically by determining the fixed points of those equations by hand. So one should always, this is again not specifically for you, that's why I want to go over it now. For anybody, when you write a set of equations like this, you should evaluate the fixed points by hand. So you can look at the equations, you know what the form is, and now you evaluate what the fixed points are. And then you can ask the question, is the fixed point correctly 10 to the minus 49th? And if so, what is the functional form of the parameters that lead to that value? But essentially what this is telling you is you reach some steady state. Whether that steady state is reasonable is hard for me to tell, but effectively your interferon level is 0. Unless there's a funny scaling going on. So it's, I think, important to think about what the equations mean before. It's useful to do a numerical solution, but once you've done the numerical solution, focus on the meaning of the equations. What is the circuit doing? What do you expect? You don't have that many. I mean, when you have a lot of feedback loops, it's not easy to do that analysis, but in this case, there are not so many feedback loops. And so you ought to be able to, and I don't mean you personally, but in general, one ought to be able to walk through this and analyze this by hand. I think what we spend a lot of time in the class doing is trying to explain how to do that kind of rough estimate by hand to get a meaningful result. If you have a numerical value that's very small, you should be able to determine where is that numerical value coming from. Is there something that looks like 10 to the minus 49th in the equations? Or is it really just that this is 0 and staying 0? Another thing that you might want to think about is instead of plotting the absolute numerical values, you might plot the values relative to their maximum concentration. So you plot the value as a percentage of the maximum, fraction of the maximum. Then they all work on the same scale. You don't have to use a log scale for it.
Okay, I'll refine it.
So there are a couple. I'm happy. Let's have a private meeting and go over this because you've made a lot of progress. But I think again, this is why I think is helpful in general. And again, for this semester, it's a little late. But in general, it's really better to work as a team. Because when one person gets stuck on something like this, the other person will often see what's going on.
Yeah.
And I think
I agree.
having a team to work together makes these things easier. Everyone wanted to do separate projects, and I respect that. But I think it's easy to get stuck. It may be that one person is stuck on a technical issue, like how do I use a slider? Somebody else is stuck on a scientific issue. And so working together, sometimes people can complement each other. I don't want to make too much of a fuss about that, but going forward, I hope that that's something we can learn from each other.
I agree. Thank you.
Okay, great. And let's meet and go over it one-on-one.
Okay.
Ibraheem.
Yeah, I guess also share this quickly. Okay, so I will. Okay, so I have been able to recreate one of the more complicated. So I was having difficulty finding values, like variable values when I was creating my own functions by like adding up different sections from different papers. So I decided just to concede and basically take one of the most complicated ones that had the most like additions from one paper, because they already had values that would allow me to I guess, get meaningful results. So I was able to recreate all 4 scenarios. This is a scenario where both predators and prey go extinct. This is a scenario where just the prey goes extinct. This is a scenario where just the predators go extinct. And then this is a scenario where they both coexist around here. So I think this is a pretty good start. What I really want to do, though, is get these sliders working so that I can do the educational part and explain how modifying the parameters, because right now the difference between these is really just parameter changes. So I kind of want to explain how modifying the different parameters will modify the phase plot. And I guess I'm trying to figure out how to get the sliders to work. That's what I've been kind of stuck on right now.
Okay. I think that's something where, well, William, it looks like you have the sliders working. So maybe, William, you could help Ibraheem a little bit. I know, Hayden, you know how to use the sliders. So again, this
Yeah,
is, you're reaching out to each other, and you look over his shoulders and give him some advice about what he's doing. He can give you some help. Pedro's pretty good on the computing side of things. Maybe you can give him some biological advice. You try to help each other.
Sorry. I can just, maybe this could help. I don't know. I'll paste in the code that I used for one slider. And so, I mean, what it does is like, it's a function, and you use like widgets. You have to import widgets, which I don't know if you already did.
This one, right?
Import IPy widgets. Yeah.
Yeah, right.
No. Yeah. And then
I asked ChatGPT and they said I need to add this line also.
no, I don't think you don't need that.
Oh, okay, even better.
You might need from here, I'll just paste it in. These are the 2 imports that I have. I don't know if, and then yeah, I mean, one is the function that gets called whenever you interact with the slider. Yeah.
Okay.
Okay, seeing that, I just have to say, if you really want to program Python, you never should import with star. This you should be explicit. It's just never.
Okay.
You shouldn't do that. I know that Herbert does this as well in his book, but just it's okay. Ask ChatGPT and program with ChatGPT. But I think really it teaches you just wrong styles. You can get an idea when you look at such code, but you really should learn proper programming. That's what I think.
I think the issue here is probably that the callback isn't working, so that you're not actually rerunning the code for the plot.
Yeah.
So so don't keep scrolling. Go show the code and stop
Yeah.
for.
This is where I have the slider.
So you create. So, but there are 2 things. One thing creates the slider,
Yeah.
and one thing handles when you change the slider.
Yeah.
And when you change the slider, you have to call the simulation that reruns the simulation and plots it again.
Okay.
I think what's happening here is, where is the actual code? The code is in this for IDX in range 200. It's down at the bottom.
Yeah.
That's not inside of the callback that is called every time you update the slider. So
okay.
all of that has to be put inside of a function, which is an update function.
Okay.
And so the syntax for this is a little bit different. So you should look at the code for one of the slider examples.
Okay, I'll do that.
Because once you have one, that's why I was asking a couple of weeks ago whether people wanted a lecture on sliders. Because once you've done it once, you can simply cut and paste whatever code does the display into that box. But the first time you do it, it's a little bit unintuitive because all of the simulation that actually does the plotting goes inside of a function,
Mm-hmm.
which is called whenever the slider is moved.
Okay, that makes sense.
So William, if you look at the demo that William has done, for example, or Hayden can supply with you, then you'll have the example for how to do that. It's not that complicated. It's only a few lines of code, but if you're not used to that, it's effectively event-driven code. If you haven't done that before, it's a little bit unusual, a little bit different from the way you'd normally do it. But you definitely, if you're seeing the for loop there up on the left-hand margin, that by definition isn't right for what you're doing. Because
Yeah, I think it should be here.
it has to be inside a code block for what you do when you update the. So you have a function slider is calling a function update text.
This one, yeah.
Right. So everything that's basically down at the bottom needs to be inside of that def update text function.
Okay, that makes sense.
Okay. And I realize it's non-trivial to get that to work the first time. So if you look in the IPyWidgets manuals, they have pretty good demos for how to do it. But again, it's not trivial to figure it out. Okay, so let me come back to where we were last week, or 2 weeks ago now. 3 weeks because of eventually I'll get it right. 3 weeks because of the holiday, which is we did started out by analyzing fixed points in one dimension, and we came up to the very simple result that if the derivative of the rate equation is positive at the fixed point, then the fixed point is unstable. And if the derivative of the rate equation is negative at the fixed point is stable. And so that was a pretty simple result in one dimension. And we did a little bit of analysis using Taylor expansion to show that you get exponential movement towards or away from the fixed point, depending on the sign of the derivative. And then we introduced the concept of bifurcations in one dimension. And there's some parameter that we change. At some critical value of the parameter, we either create or destroy fixed points or change the slope of the function at the fixed point. Those are the two ways you can do it. And we made a comment that if the rate function is smooth and differentiable, then the bifurcations always involve either the creation or disappearance of pairs of stable and unstable fixed points. And we did some exercises where we changed a parameter value, and here we've plotted the value of the rate as a function of a parameter lambda. And as that we change lambda, in this case we increase lambda, this line moves down. When it touches the x-axis, we create a neutrally stable fixed point. As we keep increasing the value of lambda, that neutrally stable fixed point splits into a stable fixed point on the left and an unstable fixed point on the right. And those fixed points move apart from each other. And then we analyzed the auto-activation circuit, which we've worked with quite a bit during this semester. And we plotted the rate law on the right-hand side of the equation, changing the value of K Basel that moves the whole circuit up and down, the line up and down, and changing the value of D1, the decay rate. And what we saw then here on the right, we've plotted the fixed points as a function of the value of K Basel and of D1. And we've used the trick of running time backwards to determine the values of the unstable fixed points, because a fixed point that's unstable in forward time is stable in backwards time. And you have a little code exercise that will do that for you now. And you probably will want those code exercises for today, for the rest of today. And what we found was that if we make K Basel small, that we have 3 fixed points a stable fixed point with a low value, stable fixed point with a high value, and an unstable intermediate fixed point. If we make K Basel too big, then we get a single stable fixed point at the high value. Notice there's no discontinuity at K Basel equals 0.2. The lower fixed points disappear, but the upper one doesn't do anything special. And what's happening there, if we look at these equations, K Basel is essentially a source of material that's being dumped into the system. If we dump material in at a big rate, then this Hill function doesn't do anything. Basically might as well not be there. It's just K Basel minus D1A, which has a fixed point of K Basel over D1. So we lose those lower stable and unstable fixed points. In this case, the lower stable and unstable fixed point collide and annihilate each other. In the case of increasing D1, what's happening is, in a sense, we're bending the curve. Instead of moving it up and down, we're twisting it around the 0 point. And so as we make D1 bigger, the curve comes down. If we make D1 equals 0, if D1 is 0, there's no decay. And that means that this thing runs off to infinity. So not very interesting. If we make D1 larger, we have an upper stable fixed point that gradually decreases. If we make D1 too big, we'll notice that our curve doesn't touch the x-axis at all anymore. And our upper stable fixed point disappears, and we just have a fixed point of 0. And this makes sense. If we have very, very rapid decay, then no matter what we do to try to produce, we get nothing. And so both of these things make sense. If we keep dumping things in very fast with K Basel, then our circuit isn't doing anything. All we have is production, dumping in of chemical and decay of the chemical. The regulation doesn't work. That's what's happening on the right-hand side of this bifurcation plot. If we get rid of the chemical very fast, no matter how much we dump in, we can't keep up with the elimination. We wind up with none. And that's what happens here. If D1 is 0, the stable fixed point is infinity, which we can't plot. As we increase D1, that stable fixed point, upper stable fixed point, comes down rapidly. The lower stable fixed point is always 0. The unstable intermediate point gradually goes up. It will collide with the stable fixed point on its way down, annihilate, and you'll have only the stable fixed point at 0. And so again, looking at the plot of the right-hand side, the rate as a function of these parameters, we can see what's happening, why we're getting the bifurcation diagram that we are. We did a little bit of mathematics, which we skipped through pretty fast because I didn't really want to go through canonical forms in great detail. If we were in a math department, we'd spend a lot of time on that. And we found that there were 4 kinds of bifurcations in one dimension. One that looked like lambda minus x squared, which gives us a saddle node or tangent bifurcation, where on the left we have no fixed points. On the right, we create one stable and one unstable fixed point. And you'll notice these move apart as x squared. So it's a parabolic separation, which is typical. We have transcritical or exchange of stability bifurcation. We have a stable fixed point at 0, an unstable fixed point at a negative value. They collide. The stable fixed point at 0 becomes unstable. The unstable fixed point along the diagonal becomes stable. So the number of fixed points doesn't change, but their stability interchanges. We have the supercritical or pitchfork bifurcation. Notice this is of order x cubed, which we have a single stable fixed point on the left that splits, just like the tangent bifurcation, into a stable and another stable fixed point, again along the parabola. And the initial stable fixed point at 0 becomes an unstable fixed point along 0 as well. And has the shape of a pitchfork, which is why it's called a pitchfork bifurcation. The subcritical one simply flips the signs of that And so we have a single stable fixed point that collides with two often unseen unstable fixed points to give us a single unstable fixed point. So those are the four one-dimensional bifurcations. And then we did a little theorem to show that, in fact, there are no periodic or chaotic solutions in one dimension. Unless we have time delays, you can't have anything except stable or unstable fixed points in 1D. And then we began to talk a little bit about higher dimensional stability. We'll come back to that in a little bit. But we simply decided that one way to write things would be to say that there's a vector which consists of all of our chemical concentrations. And there's a function, a vector function, which aggregates all of our individual functions. F1 for N1, F2 for N2, and so on. And writing things in vector form changes our notation a little bit, but it's going to make things a little bit easier when we want to do the mathematics instead of having each one have its own name. Again, the concept of stability, if we start from a fixed point and we move away from that fixed point a short distance in any direction, if it moves away from the fixed point, it's unstable. If it moves back to the fixed point, it's stable. And now I want to come back to where we left last time. We had started talking about null clines and flows. And this is a critical set of methodologies. We ran through it very quickly last time. I want to go back over them and do the exercises today in some detail. Fixed points tell us something about the local behavior. It tells us that if we start at a fixed point, stability fixed points tells us something about local behavior. If we start at a fixed point and it's stable, we move a little bit away, we come back. If we move a little bit, if it's unstable, we move a little bit away, we move further away. But it doesn't tell us what happens on the long term. Do we go to infinity? Do we go to another fixed point? Do we oscillate? What happens? And null-Cline analysis and plot and flow diagrams are techniques for trying to do global analysis of systems rather than just local analysis of systems. And the key idea here is something very simple, which is a null-Cline. And the null-Cline is the set of points where each individual rate is 0. So if I have dx by dt equals some function of x, y, and z, the set of all x, y, and z for which that function on the right is 0 is the null-Cline for x. Similarly for y and z. And so to solve the null-Clines, and at the moment we have to do this by hand, we don't have any way of doing it numerically or symbolically because of the way we were doing things. We have to go through our equations, set each equation to 0 by hand, and find the values of x and y and potentially z for which that right-hand side is 0. And if you look in Herbert's examples, he's done that by hand for examples where he plots the null-Clines. The great thing about a null-Cline is if dx by dt is 0, we know that the movement, whatever the direction of movement is, it's not in the x direction. Similarly for y and z. And so we know the direction of flow of our values at a null-Cline. It's perpendicular to the direction which you call the null-Cline. So the x null-Cline, the flow is perpendicular to the x direction. The y null-Cline, the flow is perpendicular to the y direction. When null-Clines cross, you get fixed points. And so I'm going to remind you of the general procedure that we're going to go through for null-Clines. We did this last 3 weeks ago, but in a little bit of a hurry. The first thing you do is if you have some series of rate equations, for each rate equation, you take the right-hand side, the rate law, and you set it to 0, and you find its roots. You might solve x in terms of y, or y in terms of x. Or it may be something complicated where you have to have some implicit form. But in any case, you have to find analytically, if possible, the set of values of each variable, which give you a 0 for that particular rate equation. Then you want to draw that, sketch that, and you want to label it because you have to remember which null-cline is for which variable. So if you've done it for u, you label the u null-cline du dt equals 0. You've done it for v, you label that dv dt equals 0, because otherwise you won't remember what direction you need to go. And then the next thing you're going to do is you don't know the direction of movement yet, so you'll sketch little bidirectional arrows across the null-cline, remembering that for the u null-cline, you draw the lines perpendicular to u. For the v null-cline, you draw the lines perpendicular to v, the x null-cline perpendicular to x. It's tempting to want to draw the lines to be perpendicular to the null-cline, but they're not. They're perpendicular to the axis. And we'll see in a few minutes that that makes a difference. Sometimes it makes it actually rather hard to draw. Okay. And then we have to find one spot, any one point, anywhere in our world where we can evaluate the direction of movement. Could be 0, 0, or 0, 1, or 1, 1, anywhere where the direction of movement is easy. Actually, we don't really want 1, 1 because there it's 0. And we draw that direction and we label it with an arrow. And then we derive all the directions across each null-cline. And we remember that when we cross the x null-cline, the direction of movement in the x direction goes from positive to negative. When we cross the y null-cline, the direction of movement in the y direction goes from positive to negative. So if we started out with, say here, in this quadrant, u is increasing and v is increasing. If we go up, we cross the u null-cline. So if u was increasing before, u is now decreasing. But v is still increasing because we didn't cross the v null-cline. And so we have to remember that. It takes a little bit of practice to remember which one flips where. But based on that, once we've drawn one arrow, we can draw the arrows in every quadrant, in every domain, just systematically flipping them whenever we cross the null-cline. And that now gives us essentially a global map of what's happening in the system. We then label the quadrants, again, so we don't forget. dv dt is greater than 0, du dt is less than 0. dv dt and du dt are both greater than 0. So we put a label in each quadrant. And then we want to remember something else, which is that du dt increases in magnitude as you move away from the u null-cline, and dv dt increases in magnitude as you move away from the v null-cline. So we started out, actually I don't have that here in this particular slide, drawing all of these arrows. First, we didn't know the direction. So we now have determined the direction of each arrow, and now we know that near a fixed point, those arrows are short. As you move away from the fixed point, they get longer. Okay. And this now gives us a flow diagram for the system. And then we're done as far as we can be by hand, analytically. And then we begin to do things numerically. But when I was talking to Pedro about doing the analysis by hand, you should do this kind of analysis for your problems by hand before you start doing computation. Because once you've done this by hand, you know how the system behaves. It's not that there can't be surprises, but you've got the basics. Now, you should have code that I gave you 3 weeks ago that will plot the orbits. We did the code for that. We did it for a more complicated case. We did it for a latch, but you've got that code. And so now I would like us to walk through again, begin with, maybe be a little faster this time. I'd like you to do the null-Cline derivation again in class. And we're going to start out with the Lotka-Volterra equations. These are the classic simple predator-prey equations that every class in mathematical biology starts out with. They're more than 100 years old, that were the beginning of mathematical biology in the context of population dynamics. And the equations are du by dt is equal to u times 1 minus v, and dv by dt equals alpha times v times u minus 1. And so the first thing you want to do is, what are the u null-clines? The u null-clines you get by setting 0 equals u times 1 minus v. The v null-clines you get by setting 0 equals alpha v times u minus 1. Notice that any set of points where u and v give 0 is part of the u null-cline. And so it's possible, if you have a product, that you could have multiple lines that are all part of the same null-cline. It doesn't have to be a single line. And that's an example here. Let's just look at this. The u null-cline, if u is 0, the right-hand side is 0, right? No matter what the value of v is. And so u comma v, 0 comma v is one null-cline. But there's a second null-cline, which is no matter what the value of u is, if v is equal to 1, the right-hand side is 0. So u comma 1 is also a null-cline. So the u null-cline actually consists of two sets, the set of 0 comma v and the set of u comma 1. There are two lines, not one. So why don't people figure out the same thing for v and then write those down, write the equations down for those. They're very simple. And then draw them on a little diagram by hand, sketch them, and label which one is the u null-cline and which is the v null-cline. Okay? And then, as I say, lightly sketch with a pencil or something like that, bidirectional arrows across each null-cline. Remember that the u null-cline, the arrows are in the v direction. The v null-cline, the arrows are in the u direction. And why don't we just do that together? And give me a thumbs up in the chat when you have it drawn on a piece of paper. Okay. Okay, great. Does somebody want to show what they got? So okay, so yeah, there go your axes. Okay. So is this u and v here? Okay. So those look like the null-clines. That's fine. And somebody's already labeled the directions, which was the next step that I was going to ask. But that looks great. Okay. Did anybody have any questions about that or trouble with that?
Wait, yeah, sorry. What do we do about the other ones?
Which
Do
other
we
one?
not care about them? Are
So
these not, is this not one? Is this not one? Is this not one?
so absolutely 0 comma v, 0 comma v, which is along here, is a null-cline for u, right? So this is u dot equals 0. And let me change the color. Let's see if I can change the color. And u comma 0, this one is a null-cline for v. actually, I've got this backwards, right? U comma 0 is a null-cline for V. So this is V dot equals 0. That's why I say you really need to label them to make sure that you've got this right. This null-cline, the middle one, is horizontal. That means this is V dot equals 0. And this one is U dot equals 0. So what does this V dot equals 0 mean? It means that if you're near this line, you're horizontal. If you're near this line, U dot equals 0, you're vertical. Now, this is hard to draw because the direction of movement is parallel to the null-cline. That's what I said. You can't. It's always not always easy to draw those lines that you need. But you're right that you should be aware of that, and you're going to see that in a minute or two, why that's important. So that's a great question, William.
But what about, like, I guess in the negative U and negative V area?
Well, in this case, U and V are
Here.
always positive. We're not looking at those
Okay.
because we're talking about a population. But you're absolutely right that at least in principle, you can cross. Well, suppose we allowed U and V to go negative. Then absolutely, when we cross the V dot equals 0 null-cline, the direction of movement in V will change. And so if we're going down here, then we would be going up when we cross the V dot null-cline. And so we would be going this way here. And let's see, are there other ones that would be doing something like that? This is the V dot. Did I mislabel this? Certainly possible that I mislabeled it. Let's see. V dot null-cline, yes. So we change, when we cross this line, we change direction from up to down, which is correct. When we cross this one, we could change direction from up to down, which is correct. In this case, we were going in this direction. So we're going upwards and to the right. So here we would be going downwards and to the right. We'd be going upwards and to the right here. Oops, I lost it. Sorry. Wonder if I can undo something. Do. Upwards and to the right. So this will mirror in that direction. Let's see where we have our lines. This is this way. When we cross here, we flip this way, so this will go this way. We cross here, we're crossing a U dot null-cline. So this is going to flip in the U direction. So this would be this way. But here we're crossing the V dot null-cline. So that's going to flip in the V direction. So it's going to be, we cross here, we cross the U dot null-cline, so that's going to be like that. This one is going to flip in this is the U direction, so it flips in the U. So it's going to be downwards and to the, so it's flipping in U. So it is downwards and to the left. So it looks like that, I think. I made a mistake here, didn't I? Which one is wrong? This flips in U, this flips in U, so that's, that's correct. That's correct. So again, as William said, there are two sets of U null-clines. There's this one along the U equals 0 axis, and then there's the one that we normally work with here. And similarly for V, you have the one along the U equals 1 line, and then the one along 0. So it's a bit of a strange architecture. Actually, Lotka-Volterra for such a simple set of equations is actually rather tricky to analyze. So we have to live with that. Okay. And so we have two fixed points where these cross, we have fixed points. We have a crossing at 1, 1, and we have a crossing at 0, 0. Two fixed points. And I didn't do everything in one step. I suggested just putting vertical lines along the U dot null-Cline, not asking which direction it goes yet. In this case, you know pretty quickly which way it goes, but sometimes it's not so easy to figure that out. So just remind yourself, put the vertical lines on the U dot null-Cline. And again, no matter the shape of the null-Clines, the arrow crossing the U dot null-Cline are always parallel to the v-axis. And that makes it problematic to draw the U dot null-Cline on this vertical line because they're parallel to the line. So if I wanted to draw a black line on this dotted one here, it would be vertical. And this is something that you'll run into occasionally, where the null-Cline is essentially parallel to the line, to the flow line. We'll see that in a minute. Okay. And now I suggested what's something that people have already done. Pick an easy point where you can evaluate the direction of movement, label that point, and then the other thing you have to do, and then do what we did before, which is flip things. So once we know the direction in one place, we know that when we cross the U dot null-Cline, the direction of the arrow in the U direction flips. We cross the V null-Cline, the direction of the arrow in the V direction flips. And so people have already done this, so I'll just walk through the results here. I picked a value of U equals 0.3, V equals 1, and just plug that in. dv dt, in that case, is 1 times 0.3 minus 1 is minus 0.7 times alpha, which is less than 1. So at 0.3, 1, which is over here, V is decreasing. So the line points downward here. And once I know it's downward there, then I can go and do all of the other directions. I have to do the same thing, though. I need to know the U direction. So I know this is downward there. I now need to know something about what's happening in the, I'll do the V ones first. Now, when I cross the V dot null-Cline, I know I point up. So I have down here and up there. Now I need to know the same thing that's happening for the X direction, the U direction. And so I can pick another example. I can now label my quadrant. In this above, to the left of this, of my V dot null-Cline, dv dt is negative. So I can say both of these left-hand quadrants, dv dt is negative. Both of these right-hand quadrants, dv dt is positive. And again, U and V, it's easy to get flipped on one of them. So you have to be systematic about it. And now let's pick a case where we're going to find the value in the. All right. Now we're going to try to find a case where we want to do the same thing for the U null-Cline. Sorry, for the V null-Cline. As I say, it's easy to get U and V backwards. The V null-Cline. And so we'll pick a point where we can evaluate du by dt. A perfectly good point for that would be 1/2, 1, for example. Sorry, 1, 1/2. If I make 1, 1/2, what's happening to du dt? 1 for u times 1 minus 0.5 gives me a half. So I'm increasing along this line here, my v dot null-Cline for small values of v. And so I have a line pointing to the right. First, I put in my bylines so that I know the direction. And now I evaluate it here. I did 1 comma 0.3. That's positive. So I draw my red line, blue line to the right. I know above the u dot null-Cline, it goes to the left. So I have my left. And so now this is where you started out when you did the screen share, right? Somebody jumped ahead to this already. And now I can label my quadrants. Above the green line, I point to the left. Below the green line, I point to the right. And so now I have all of my lines across the null-Cline labeled. And then somebody did the next natural thing, which is to say, if I'm not along the null-Cline, if I'm in this quadrant here, between 0 and 1 and 0 and 1, I'm going down and to the right. So that gives me an arrow down and to the right. If I'm in the quadrant between 1 and infinity on u and 0 and 1 on v, I'm going to the right and up. If I'm in the upper quadrant, bigger than 1 on both sides, I'm going up and to the left. If I'm in this top left quadrant, v is going down, u is going down, so I'm going down and to the left. The other thing to remember is that when I move away from the fixed point, the arrows get bigger. And so I can draw the arrows as being short when they're near the fixed point, getting longer as I go farther away from the fixed point. So I've done that a little bit here. And I'm labeling the quadrants now, their identity, to remind myself. And now I'm going to put in those diagonal lines. So you guys jumped ahead of me. You did all of this already. William, go ahead.
Wait, can you explain the math, or can you make it clear why the length of the arrows increases? I'm not sure what the
It
Well,
doesn't.
Pedro says it doesn't increase.
what do you mean? I mean, there's a short arrow and then there's a long one. I mean, like,
Well, so we know that at the fixed point, the length of the arrow is 0, right? Because at the fixed point, we're not moving in either the x or the y direction. So the length of the arrow is 0 at that dot. And we know the length of the arrow is not 0 further away. And we know things are changing smoothly and continuously. So if there's if the length is this length here and it's 0 here, it has to increase as we go over there. Now, it's possible if we went very far away, it would get shorter again. It might go up a lot over a short distance and then saturate. But we know that the length of that arrow has to be 0 at the dot, and it has to be non-zero further away. It has to change continuously.
okay, maybe I don't. Well, then, but why does it have to change continuous? Or no, that makes sense. Why does it have to be non? Oh, I guess. Okay, I guess that makes sense. Okay.
Well, that's okay. I mean, why does it have to be continuous? The answer is that the functions themselves are infinitely differentiable. If we had like a piecewise linear function that wasn't differentiable, then these things don't have to be continuous. Or if the rate constant had jumps in it, then it wouldn't have to be continuous. But in this case, it is.
Okay. Yeah. I mean. Okay. Yeah. Yep.
I agree. In some ways, it feels almost embarrassingly simple. On the other hand, it's rather slippery. It's easy to flip the direction in the wrong direction when you cross a null-Cline. You flip it in the x direction when you should flip it in the y, for example. Or it's easy to say it should be smaller here, bigger there. So it's partly because it's so simple, it's really easy to get it backwards.
I was gonna say, well, I mean, this is just the sort of diagram-y version, isn't the actual? Wouldn't it be like circles or something like that?
So that's your next step, is going to be doing that. The code we did 3 weeks ago, remember we drew the phase diagrams for things. So the next step will be using that code and changing it to do this. So here we're just going through and drawing our arrows and finishing up, which is what everyone had already. So you guys did this in a big hurry, much faster than I did. But we label the quadrants. Quadrant 1, U decreasing, V decreasing. Quadrant 2, U increasing, V decreasing. Quadrant 3, U increasing, V increasing. Quadrant 4, U decreasing, V decreasing. And as you pointed out, there are additional quadrants, because when we go over here to the left, we're crossing a null-cline. So if we allowed U and V to go negative, we have additional directions that we have to worry about, which are of interest, which we did a little bit on that on this white. So now I'd like people to take the code that we had that drew the phase portraits and try running that for the very simple Lotka-Volterra equations. And the reason I'd like you to do this is I'd like you to compare the actual orbits to the ones that we've sketched. See how similar or different they are. And the code that I've given you will calculate the orbits. I'm going to show you on the slides also things where I've calculated the flow at each point separately. And one could easily write code that would plot that. But I haven't given you that code. I don't think I want to take the time today. That's something that would be a good exercise if somebody wants to write a little 2 lines of code to generate those plots as well. That would be great. Okay, but is the assignment now clear? Take the code that we remember. We did the code for the latch. We had a workbook that would plot the latch. And now, instead of using that more complicated set of differential equations, use this very simple set for Lotka-Volterra. Does anybody want to try, instead of running between 0 and 4, try making your plot go from -1, your x range and y range go from -1 to 4, so you can see what happens in those quadrants that are on the other side that we were talking about. You probably still want to go up to 4 on the positive side because you want to see that closed cycle. There you go. Perfect. Let me just walk through the result without that extra quadrant, because actually I should put that extra quadrant into the slides. So I think you're right to make the point that that's important. So I did these slides quite a while ago, before we had the code that we have now, and I used the code called XPP odd, which is by Bart Ehrmantraut, and it allows you to do 2 things. It'll allow you to evaluate the flow at each point, which is what you're seeing here. So here at each point, I'm showing the equivalent of the little blue arrow that I've drawn by hand. And this is the flow diagram. And actually that's used in the calculation of the orbit diagram that we have here. And that's for the one I said we didn't have plotted. We're actually calculating that because when we call line 21 and 22 in the code and calculate U and capital V, that's calculating the derivatives. And so we could, in fact, plot the little vectors. And I'd have to look up how to do that. Maybe somebody, if you're ahead of us, somebody who's already got this working could do that. And then the orbit calculation is here on the right. And this is what Pedro and I think Ibraheem also had shared in the chat. Ibraheem and Pedro also have the nice put up the null clines on the plot, which is very nice. The XPP didn't give me the null clines. And you'll notice that if I compare this to my sketch, near the fixed point, it's basically a circle, so that's pretty good. But when I get near the x equals 0 or y equals 0 lines, the shape is rather different, right? Things get distorted. It looks a little bit like a clamshell. And if we look at Pedro's picture, which is very nice, we'll see that more clearly perhaps than what I've got plotted here. Something that is worth mentioning, and we're going to see this more in a few minutes, is that what are called the Lagrangian versus the Eulerian formalism. In one case, I evaluated each point, what direction I'd move. In the other case, I take a single point and I follow its trajectory in time. In some ways, they're giving me the same information. In some ways, they're giving me slightly different information. In the case of Lotka-Volterra, if I look at the left and the right, I can immediately translate one to the other. I'm going to find that for more complicated flows, it's not always so easy to translate back and forth. Okay. Are there any questions? Any questions about this before we move on? I want to make sure that everybody has this basic code working because we're going to use this code again in the next exercise.
I have a question to this orbit.
Yes.
So these circles that you have,
Yes.
they are not trajectories.
Yes, they are trajectories.
They are trajectories. But that means that if they're like this, then they are oscillating, then they are not going to the 0 point where they're not move anymore.
Right. Well, Lotka-Volterra is neutrally stable. The fixed points are neutrally stable. So Lotka-Volterra is a little bit of a strange equation because it's linear. It's linear in U and in V. And so the fixed point at 1, 1 is neutrally stable. It's not stable or unstable.
So it means that you have oscillation that never ends, and when you start high, you will keep high oscillation, and when you keep with a low oscillation, you will
If I
keep low
start
oscillation.
if I start on one of these circles, I stay on the circle forever.
Circle. Yes, yeah.
If I perturb off of the circle, I stay on wherever I am on my new circle. I don't come back.
Yeah.
And so
Yes.
so I don't
Yes.
so Lotka-Volterra is not really a very good example of stability because it's in fact really stable.
It's just stable everywhere, kind of.
But it's neutrally stable. If I make a perturbation, I don't come back. I always stay wherever if I move myself to a new place, I stay there.
Yeah. Interesting. I mean, I know chaotic attractors and I know attractors that somehow
right. There are no
go
attractors.
into that they circle or that they go to a fixed point, but this one is kind of very special. I see this first time.
There are no attractors for Lotka-Volterra. Because it's not disciplined. It's conservative.
This is not attracted, these are just trajectories.
That's right. There's no dissipation. There is no dissipation in Lotka-Volterra. It's
okay, this clarifies a lot for my general understanding. Nice. Thank you.
That's why I'm not wild about it as a first example, because it's rather atypical of the kinds of things we do. But historically, it was the first one that was done, and mathematically, it's the simplest one. So people use that as their first example. Okay. So now, remind you, just to review again, find the null clines for each equation independently, draw and label them, sketch the bidirectional arrows, pick a point to evaluate the direction of movement, label the point, and then systematically check the directions that you change when you cross the null clines, label all of the arrows correctly. So instead of being bidirectional, make them unidirectional. Label your quadrants and adjust the arrow lengths and then sketch. That's what we have to do. So now, do people want to take a 5-minute break, or do you want to do one more exercise?
I need the code, but yeah, a 5-minute break would be good too.
Okay, so for the code, you didn't get it from the chat. I shared it in the chat.
No.
You updated.
I didn't. Yeah, I mean, I didn't get it. I don't know how to do it.
Pedro, could you share your code in the chat? The note?
Sure.
And then William, if you want to try to make sure, because I don't want anybody to get lost. And
Yeah.
then our next exercise, when we come back at 6 o'clock, will be changing this by exactly one thing. Instead of having it u times 1 minus v, it'll be u times 1 minus v squared. And instead of alpha v times u minus 1, it'll be alpha v times u squared minus 1. And now it's going to have fixed points that are stable or unstable, and cycles that are stable or unstable.
And actually, because I always thought the simplest one of this quadratic equation, okay, that get chaotic, would be the what is it, the logistic equation? I mean, could you study?
So the logistic equation is one-dimensional, so now we're in 2 dimensions.
Yeah, true.
But this has the form, this looks, so the Lotka-Volterra equation looks a little bit like a logistic equation, except they're cross terms. To get something that's non-trivial in 2 dimensions, you have to have a quadratic in at least one of the variables. So, okay, so let's take a 5-minute break. Pedro, did you share? William, did you get your?
Yeah, I got it. Thank you.
Okay, so why don't you try playing with it over the break? Try to get that Lotka-Volterra to work. William, were you able to get that to work?
Ah. I disagree, Ibrahim.
In what way?
Wait a second, I'm thinking. Yeah, I disagree. So
With which part?
in this one here, I will raise in a second. In
Okay.
this Null-Cline right here, U equals 1. And this is the U equals 1 is no, sorry. Let's go back. Let me take this one, V equals 1. For V equals 1, okay, yeah, that makes sense. No, I have to think a little bit more. Yeah, that's right. Yeah, so the limit the cycle, the limit cycle is okay.
So it looks good, right?
Yeah, now I'm thinking about close to the V and U axis.
Mm-hmm.
think that's it. Yeah.
Okay, how's it going? Everybody got this working? Yeah, somebody did all the extra ones, which is nice. Does somebody want to show let me, so you've got two cycles. The upper right-hand quadrant cycle looks the way it did before. And then you've got these mirrors that are coming in the upper left for negatives values, with the directions reversed. So that's great. That's more than I actually planned on doing. So let's clear this for a second and let's see what we got. Let's clear it and see what we got. So this is the upper right quadrant. You'll notice the upper right quadrant looks very much like the Lotka-Volterra. But there's a significant difference. And the significant difference is in the stability, which we can see in a minute. So does somebody want to show, did somebody do the full plot? Pedro, maybe? Do you want to show what you got when you did the 4 quadrants?
In the Python?
Yeah, the numerical result.
Yep. Give me 2 seconds. There we go.
Why don't you screen share it?
Yeah.
Okay, and in this one, you probably want to change your x-axis to be -5 to 5, or why don't you make the x-axis -3 to 3 and y-axis -3 to 3?
Sure.
So we can see the symmetry better.
Pedro, I think you might have squared the wrong ones.
Square the wrong what?
I think we're the 1 minus y. It's supposed to be 1 minus y squared instead of x squared.
Oh yeah, this is flipped, isn't it? It's a
Ah,
different equation.
thank you.
It's interesting, but not the same.
I'm under the influence. Okay.
Okay, great. And so now if we wanted to finish this up, we'd have to add those extra null clines by hand.
Mhm.
To make it work. Does everybody get this to work, or are people still working on it? Again, I realize the first few times you do this, it's tricky. Well, the reason we're doing that repeated exercises is so that you have a chance to gradually work up the complexity of the problem. There we go. I think the colors are not quite right for the null clines, but that's okay. Does anybody need help with that, or did everybody get something that looked like that? In general, I only have been looking at the positive plane because I've been assuming that we had the positive amounts of the species, but you're right. Mathematically, there's no reason not to look at the negative side too.
No, I think the null clines are right.
Okay. I mean, something that's not so clear from this one is whether this is neutrally stable or not. I believe this is still neutrally stable because if I look at the orbits, I'm not seeing spirals. I'm seeing closed circles. And so that means I'm still neutrally stable. This still has the problems that Lotka-Volterra has. Okay, great.
Are you saying if we plot this as a time series till infinity, it will never converge to zero?
That's right. Why doesn't somebody try that while you're at it and tell me what you get? You should see the oscillations should continue forever. Now you could have a limit cycle where you do get oscillations, but then for different initial conditions, you should still converge to the same limit cycle. For this case, for different initial conditions, you'll always see the same. The oscillation won't change in time.
Can I share? I get kind of oscillation, but it's very like it's not sinuous. And I don't understand why.
I think I have the same thing as you, Elmar. I can show it if you
Yes,
wanna
maybe
explain.
you could share. And I wonder why, because it's circular. Why do we have this sharp peak right from?
Yeah.
It's kind of when it goes to 7, then the X and the Y. So, it's always one X and one Y and one.
Well, so when we
We
draw
have to do a plotting
when we
spatial.
draw- when we draw the orbits, we don't know how fast we're moving, do we? Right? We could be moving slowly and for some time fast for another. So we're going around the loop, but we don't know how rapidly we're going.
But if you're farther away from our incline point, we get faster when we're farther away, like planets.
Here, this is, I think, the plot you're referencing, right?
Yeah.
Yes. And I wonder if we would have to plot it in X and Y as well. No, because then we have to circle again.
I'm a little puzzled by what's going on there. It looks like what happens is when it gets close to 0, the velocity is very fast. So you're just plotting X versus time and Y versus time for this?
Yep.
So Y-axis should be X-axis should be time and Y should be.
Yeah, well, you see, if you look at this, if you look at the diagram here, you always get very close to X equals 0 and Y equals 0. And then you move very rapidly along those. So that seems to be correct. Why don't we try it? Let's go back where you define the function. Let's go back to Lotka-Volterra and just get rid of the squares and see what we get.
Okay, I have to move my microphone.
It might also be because I picked a very large starting X and starting Y. If it's closer to the center, it might not be as extreme.
We could try that. That would be a good thing to do. But let's do Lotka-Volterra first. And that should be smoother. So it's still pretty fast. Okay, why don't we try something near 1, 1, like 1.1 and 1.1, 1.1. See, that's much better behaved.
Yeah.
That's almost sinusoidal. And now as you move further and further away, because you can't cross 0. So if it's trying to get to 0, it gets stuck. That's why having those Null-Clines that are apparently in the wrong direction make a big difference. So why don't we try 1.5, say, instead of 1. Yeah. See, it's still behaving pretty well.
Just so that we can see it better.
And it's just, okay, so that's very well behaved. Now put the squareds back and see what happens. See, there's a lot you can do with these very simple systems. They're already not trivial to analyze. Okay, so it's still pretty well behaved, but you notice it's beginning to get asymmetrical between the top and the bottom.
Mm-hmm.
And now as you keep pushing it, when you get towards 0, it's going to get faster and steeper. The top will still be well behaved, but the bottom will get strange. So now you could try to say 2 for your initial condition. So what your results are in fact correct, and there's nothing strange going on. What you're seeing is really the fact that you're getting crowded at 0. You see now it's getting quite bent, quite stiff at 0. Yeah, very nice. So I should probably have asked you to plot the time series as well in my analysis. Okay, great.
And I could do a slider for your.
That would be great if somebody wants to add a slide. William, were you able to get this to run now? Were you able to run the code that was shared?
Yeah, yep, it's all good. I got it. I'm good.
I'm really glad that people are working together on this. This is great. Okay, so we got that one. So now let's try this one. Doesn't look like a huge difference, right?
Like a mess, actually.
Well, calculating the null clines by hand takes a little bit more work this time. Not a lot. What I do need is to add the ones that plot the vectors at the points rather than just the orbits, because I don't have the thing set up to plot that. That plot vector field will do it, but I just have to set it up. Maybe somebody can, if somebody is ahead of the rest of the class, they can look up how to do that plot. Yep. So again, there are 2 null clines for each, for U and for V, as before. Yep. Yep. Perfect. Okay, so now you have to remember what direction is the flow when you cross the U dot null cline. Are you vertical or horizontal? When you cross the U dot null cline, you're vertical.
Yes.
Okay, so now let's find a place on the U dot null cline and see whether we're going to the up or down. Let's see, is that right? The red is
Oh, I messed up. I messed up.
backwards. That's backwards. See, that's what I say. It's easy to go backwards to this. That's why we do it together to practice. Okay. Okay, great. And now we have to see what direction. So you could pick a point which is easy, like U equals 1, V equals 1/2, and calculate what direction you are. If U equals 1 and V equals 1/2, then du dt is equal to 1 minus 1/2 is 1/2. So du dt is positive. So U equals 1, V equals 1/2 is positive in U. So you could draw something there and then figure the rest of it.
Isn't it? Wait.
Question?
Like this? Weird. Okay, it makes sense.
That's fine. And so what about on the V Null-Cline? Okay, good. All right. So that's a proposal. So does somebody now want to put it into the computer and see what you got? Here's my hand. Well, that's I don't want to give it away. This one is the first one that's a little more interesting. And somebody could plot the time series too. It would be useful to have the time series. In this case, by the way, you are not going to want to plot the negative values. You can tell me why after you try it. William, can you plug this into the code and see what you get for the phase plot?
Yeah, I had it with negatives. I'm just changing it now. I could share.
Well, I mean, you can try with negatives. Let's see what you got.
I don't.
It may blow up if you use negative numbers. That's what may happen.
Well, yeah. I mean, I just didn't get the null-cline, the actual null-clines.
That's okay.
I didn't
Just plot
manually do that,
just plot
but
the orbitals. Yeah, that's fine. It takes
that-
time to
that's
type
it.
in the Null-Cline ones.
Oh.
You're showing the lecture. No.
Wait, this.
Yeah, there you go. Okay, good. So for this one, why don't you turn off the Null-Clines because they're a little bit confusing to see there. Good. Okay, now. Okay, perfect.
I know I changed it. Yeah.
Okay,
Yeah.
good. So what do you see happening here? Can somebody tell me what you're seeing? If we saw the time series, it might be easier.
Yeah, now you have an attractor. Now it goes to 1-1. It's the attractor. Wow.
Right, so 1-1 is now a stable fixed point.
Yeah.
But you'll notice there's still oscillations, but they're damped oscillations. You're almost going around in a circle, but you're decaying to the center. Wherever you start, you're going to wind up at 1-1. But if you start, just pick a value, pick some point to start with, any place on the screen to start with, on one line, maybe one of the ones that, yeah, there you go. So now what's happening? Y is decreasing, X is decreasing a little bit, and then you cross that Null-Cline, and X starts increasing and Y is still decreasing. You come down. It's a little more obvious. Why don't you start in the lower near 0,0? Right here, X is increasing, Y is increasing. Now X starts decreasing and Y is still increasing. And you overshoot just a little bit and then Y starts decreasing again. So what you have is a very strongly damped oscillation to that fixed point. Okay, did everybody get that? And I understand if you plot the time series, next to this. Maybe it's worth plotting the time series as well.
I pasted one in chat.
Great. But you should see that for every initial condition you wind up with. Yeah, there we go. See, it overshoots a little bit and then comes back. Yeah, that's very nice.
Okay. Yeah, I'm just gonna stop sharing. Wait, sorry.
Okay, great.
I
Ibraheem
wanna
has
put
it
this-
in the chat.
No, yeah. Sorry, I'm stopping.
Yeah, that's
Okay.
it. No, what you showed is right. It just
Oh, okay.
changed the
Oh,
time.
the x-axis.
The x-axis is. Why don't you just run it for a shorter time and redisplay it so everybody can see it? The one reason I'd like the people to display it is because for the recording, the chat's not visible for people online. So there you go. Perfect. So that's what it looks like. So again, translating back and forth between these phase plots or these orbit plots and the time series takes a little bit of getting used to too. But that's great. I think people beginning to get the hang of it. I think everybody's gotten it working now, huh? That's great. So let me come back and I'm really it's not trivial to get used to these null clines. It takes some practice. Okay, so that's what we got. It looks great. Again, the general procedure. So I'm going to skip this exercise, but if I drew some weird set of null clines and just labeled them, du by dt is 0, dv by dt is 0, and I give you one arrow, then you can label each quadrant. You can do each time you cross du dt, you flip the direction in u. Each time you cross dv dt, you flip the direction in v. So even if I don't give you an equation, if I just give you the null clines in one arrow, you can draw the flow everywhere. That's why it's so powerful. Does that make sense to people? Because I know what happens each time I cross the red line, I flip in the v direction. Each time I cross the green line, I flip in the u direction. So I know the behavior everywhere. So this is now a global analysis rather than a local analysis. Yes.
Wait, do you flip it perpendicular to where you are on that line, right? Like,
If
no?
here, if I start out, I'm decreasing in v,
Yeah.
I'm increasing in u. If I cross the green line, I don't change the direction in v, but I do change the direction in u. If I cross the red line, I change the direction in v, but not in u.
Okay.
So, okay, actually, why don't we do it? Somebody, you can all annotate. Why don't somebody draw, what's the arrow direction in this quadrant here above the red line? Somebody just draw on top of this, the arrow. I'm crossing, I start out increasing u, decreasing v. I'm crossing the v null-cline. So v will now be increasing and u will be still increasing. So let me add the annotation. Can people annotate? I think you can all annotate. Yeah, so you're going, be careful not to cross that other null-cline though, because it changes direction on the null-cline. Yeah, there we go. Elmar, yeah, so Elmar has this. Good. Okay. What about crossing up here? When I cross going this way, I'm crossing the du null-cline, so now I go backwards in u. So I'm increasing, so that one goes like that. What about here in this quadrant? What about in this here? Which direction do I go? I've crossed the u null-cline, so v is still decreasing, but u is now decreasing as well. There. Okay, good. What about here? Remember, everywhere inside, if I don't cross the null cline, I'm always going in the same direction, maybe a different angle, but that's still that one. Yeah, that's right. So what about here? I've crossed the V null cline, so the V direction changes and the U doesn't. So the V direction goes from down to up. If it were this one, it wouldn't have changed because it goes from here is down and left, right, and this is still down and right. So that can't be right. The V direction changes, so it's up and right. Yes, there you go. And the last part is here. What's that? Here I've crossed the U null cline, so it's down and yep, that's right. So you've got all of them. Now, figuring out what the flows would look like takes a little bit of work. You have to say you're going up here, that way, this way. We haven't talked about these bifurcations yet, what kind of fixed points these are, but we can do that. But you're able to label it all. And then if you notice that the lines get longer as you go further away, you can get a rough estimate of what the flow looks like. Good, great. All right. Okay, so I want to do one more example tonight, which is one that's more important. Well, to be fair, Lotka-Volterra is very important. Historically, that was a very important equation, but we don't use it for much anymore. But I want to come back to something called the Fitts-Unagumo equation. Fitts-Unagumo equation is one that really gets used. And this is a model of the electrical potential of neurons. And in this case, we're modeling the potassium and sodium concentrations inside of the neuron. And for the purposes of this class, I'm afraid I'm not going to be able to go over the reason for the equations having the form they do. Although, if you're interested, Wikipedia has a very good article on it. But it has a slightly more complex form than the ones we've looked at. In particular, you'll notice this is cubic. The U equation looks like U times U times U. So it's a cubic equation. And that means the U null cline goes down and comes up and goes down again. It's a cubic. The V equation, U minus C minus B times V, is linear in U and V. So it's very simple. It's a straight line. All right. So why don't people try, and again, you're welcome to do this on the screen instead of doing it on a piece of paper if you want. Why don't people try to label the fixed points and the direction of flow on the null clines? And we're starting out with C equals 0. First, looking at this picture, there are definitely some additional null clines here. For example, U equals 0 is, sorry, that's actually wrong. I've got to be careful here. There's only one null cline for V. And let's see, are there any non-trivial null clines besides the ones I've drawn? I think the answer actually is no in this case. So I think there are only these null clines. So does anybody want to, so how many fixed points are there? Anybody?
It's not only one, the one that the line's crossing.
Where it crosses, perfect. Okay,
Could be two, but I mean, depends on. It could be three even.
well, for this particular set of parameter values,
Yeah.
okay, yeah, those are all possible if I change my parameters, but I just meant for this set of parameters.
Mhm.
Perfect. And what about the directions of flow?
Pedro, can you explain when it would be 3?
So it's basically the green. I'm changing the green line.
Right, and you would do that,
When you go down and then you
Yes.
cross as well the other ones, like, yeah. Okay, yeah, got you. Thank you.
if you change the value of B, you're going to change the angle of this line, right? Because the U-Null-Cline is a little hard to evaluate. Well, it's actually not hard to evaluate. The U-Null-Cline is just U equals V equals this, right? So you can actually do it analytically very easily. If I sweep U and set V equal to U times U minus A times 1 minus U, I get the U-Null-Cline. I don't have to do any fancy math. For V, if C is 0, then the V-Null-Cline is simply V equals U over B, right? And so if I make B large, this gets shallower. So if I make B bigger, this line gets, the slope gets like that as Pedro drew. But we're not gonna play with that right at the moment. So why don't people just sketch for me the null-clines for this? What direction on the dv/dt null-cline? I'm going which direction, horizontally or vertically? Horizontally, good. On the U-Null-Cline, I'm going horizontally or vertically? Vertically, good. And now, which am I going up or down? Pick a point which you can evaluate. dv/dt is a good one to start with. Am I going up or down? If U is positive and V is small, then I'm going up. So if U is positive and V is small, I'm going up. So can somebody put the arrows on those lines that Pedro's drawn? Okay. Now what about the horizontal ones? Are they going to the left or the right? Okay. Good. All right. Very good. So does somebody now want to take the code that they've got? First, give me a time series. Plot the time series for U for these equations, and then plot the orbits. And this is actually quite an interesting one. So I'd like people to try that together. And I should point out that in this case, we're actually talking about, I said that the ionic concentrations, it's really electrical potential that's representing the ionic concentration. The electrical potential can be either positive or negative. So in fact, in this case, the values really do go between plus and minus numbers. And if somebody has the time series, they could show that. And if somebody has the phase portrait, that would be great too. In the first place, but let me ask a question. There's only one fixed point, so how complicated can this be?
Almost
I
no
got it.
complication. I mean,
If there's only one fixed point, you think it's going to be fairly trivial.
Yeah.
Well, what did you get? Does somebody have a time series for this?
I got that to be a time series.
Okay, let's see.
Is that wrong?
It doesn't look quite like what I'm expecting.
That's the phase.
The phase portrait, something is not quite right about your equations. Let's come back to the equations. Let's see. Can we zoom in a little bit? Maybe make that bigger, and can we check to see whether everybody look at those together? So you have x times x minus 0.5 times y. That looks right. And the first one is x times x minus 1 point x minus u. Okay. Let's see, where's the 0.1 coming from?
Wasn't that a value for, what was it, C maybe? Or one of them?
Okay, so
Right.
let me put, so there's one thing that's a slight trick here, which is let me screen share again.
Yeah.
And let me come back to this. There's something I should have pointed out perhaps, because I wasn't planning. Originally, I thought it would take people more time to do the manual things. So I was going to do this in steps. You'll notice that on the U equation, du dt is multiplied by
Oh,
0.1. So that means
see that.
on the right-hand side, if you're going to do this, it's du dt equals 100 times everything on the right.
Oops.
And that winds up actually being important. If you don't have that, it won't work. Okay.
Wait, what? Okay.
So just if you multiply both the first term and the second term by 100, then that'll give you the equations you need.
I think I can show it.
Okay. And William, why don't you work on it while we're taking a look at that?
All right.
There we go. That looks more like it.
So according to, no, this is not a spatial model.
And let's just plot U, don't plot V on the same plot. Oops.
What
You
is this?
It's because you're only putting out X. You need to put out T and X. There you go. There we go. Okay. That still doesn't look quite right to me. Start with an initial value of U of 0 or X of 0. Okay, and now run it.
Just start at some value, don't it? Because
And start with Y between minus 0.2 and 0.2. Winds up that this whole thing operates over a fairly small dynamic range. Okay, there we go. There we go. That's looking better. Okay, now what you'd like to do is, yeah, okay, you can, fine. Okay. That one is okay. So now what you want to do is scan for different initial values of V between minus 0.2 and 0.2. I had a little assignment for you, but we're going to skip ahead. Or maybe let me screen share while you're working on that, okay? Okay. I mean, what you're doing is great, but it'll take us a little while to do it. And we're going to run out of time. I want to make sure we get through this. Okay, so here's what we started with. Here's our U Null-Cline and our V Null-Cline. Okay, now we know that on the V it's horizontal, U it's vertical. And we know our left and right arrows look like this. So we're basically having a cycle that's going around counterclockwise around that fixed point, right? Now to do the flow in more detail, I could evaluate those arrows numerically, which I've done here. And now what you'd like to do is sketch the orbits, what happens in time. And the orbits are actually quite interesting. This is the case. Remember, I said drawing the arrows from a given position and looking at the flows is rather different. You get this thing that looks a little bit like an elaborate snail shell. And there's some rather interesting, sorry, yes? Go ahead.
Oh, sorry, I wasn't.
No, Pedro, go ahead.
No, I was impressed by the orbits. That's all.
So maybe somebody would like to try to generate those orbits using the code that you've got. But I'm going to walk you through things. The key thing that's happening is actually not so easy to see, but there are a couple of things that are interesting. One of the things that you'll see is that you'll see bundling. You see lots of different orbits that come together along this black line that's coming from U equals 1 going up and to the left a little initially and then horizontally and then coming down vertically and then to the right. So for lots and lots of different initial conditions, you wind up on that same set of trajectories. That's what's called an attractor. It's a very strong attractor. The second thing that's interesting, which may be harder to see, is that there's only one fixed point, and that's this one at 0, 0, and it's stable. So no matter where you start, you wind up at 0, 0. But you get there in very different ways, and this is why doing the time series is interesting. Suppose that I start at a value of U equals minus 0.5 and V equals 0.1. If I do that, and let me turn on annotation so I can sketch this. If I do that, suppose I started here. I'm going to flow right into 0. So what's going to happen? My V value will go down a little bit. My U value will go up till it's 0, and then it stops. Very boring. What happens if I start here? Very nearby, but UV equals just a little bit negative instead of positive. What is going to happen? Does somebody want to sketch what I'm going to do? What my trajectory is going to be?
No.
That's right. I'm going to zoom way over. I'm going to overshoot. I'm going to come way over here. I'm going to come up and come back and then come down again. Now, if I started right on this bundle here, I wouldn't do that big overshoot. I'd come along this line here. Down. And then I'd still come down there. So if I start for U equals negative and V positive, I see V goes down, U increases, and I go to 0. Very boring. If I start with U negative and V negative, my U value shoots up, my V value shoots up, and then I come back to 0. Okay.
I have some questions. So when they are in this channel, the trajectories, are they in the same channel or are they not touching each other? The trajectories. And this is one question. And the other one, why is it only working on a very, very small window? You said we cannot take too high values.
Well, because everything that's interesting is happening around this fixed point. If I
For
go
the time series.
right, if you notice there's this heavy braided line, which comes from 1 going up and then around.
Mhm.
If I start with very large values, I'm basically going to come back to that. If I start with very small values, I'm going to come back to it. And I won't be able to see things. In other words, if I put things on a very big scale, everything will basically collapse and I won't see that what's really going on around that circle.
I see. Yeah.
So it's not that it's wrong to do that. It just won't tell you what's interesting. You won't see it.
Yeah.
Okay. Can anybody tell me why this might be appropriate for a neuron? What do neurons do?
I mean, they send the frequency is important, and then they fire, and
What does
it gives
firing mean?
different.
What does firing mean?
Fire means that they let calcium from one synapse to the next.
Well, this is
receptor.
specifically electrical activity, but yes. But the key thing about neurons is that that when you push them, they sit there, they don't do anything. You push them just a little bit, they fire a pulse of calcium, and then they come back where they started.
Mhm.
And that's exactly what you're getting here. If I do what's called depolarization, and ironically, this is V is the calcium level. So I've got to be a little bit careful. I'm plotting U, but I'm plotting U, but I'm starting with V. If I start with a slightly negative value of V, I get a spike of U, it overshoots, goes negative, and then comes back. If I start with a slightly positive value of V, U goes down a little bit and then comes back. And so if I push this system just a little bit negative in V, I get a spike. If I push it a little positive in V, it just comes back. And so this is what's called an excitable system. Because if I start near the fixed point, and I push it in one direction, I come back normally. If I push it just a little bit in the other direction, I shoot way far away from it, and then I come back. So locally, I'm stable. If I'm very, very close to U, 0, V, 0, I stay there, and I come right back. But if I go just a little bit further away, I go way far away and then come back. So my local analysis doesn't tell me anything about what's going to happen globally here. And this is pulse generation. This is neuronal pulse generation. And it gives me very, very fine control, because if V is just a tiny bit negative, I get a pulse. If V is positive, I don't get a pulse. And that's how action potentials work. Our whole neural computation is based on this behavior. The last thing that I was hoping people could do, and I know we're out of time, but I want to walk you through this because I'm not going to have time to come back to it next time, is what if C were 0.1? Notice that C has a minus sign in front of it. This is called depolarization. We did the equations for C equals 0. Now we're going to make C equal minus 0.1. Not a big change. If I plot the Null-Clines Does this look very different? Anybody?
Not much, but
Not much.
you're not on the deepest point.
So look very carefully at this crossing.
Yeah.
Notice that before it crossed on the left-hand side of that minimum, and now it's crossing on the right-hand side of the minimum. Remember our rule in one dimension. If you cross going down, you're stable. If you cross going up, you're unstable. In this case, that happens to be flipped. If you cross here going up, if you cross here going up, you're stable. If you cross here going down, I'll get that backwards. It's a little bit more, I can't do what I just tried to do. You actually have to look at the difference. Changing, let me just put it this way. Well, I'm going to edit out my mistake because I was trying to simplify things too much and I messed up. Switching from the left-hand side of this minimum to the right-hand side of this minimum changes the stability of the fixed point. Even though the null clines everywhere in the distance are going to be the same, the directions are going to be the same, because this point doesn't know what's going on in that little point. What happens right near
So does it spiral out now?
Yes. So here I've zoomed in, and I've switched from a stable fixed point to an unstable fixed point. If I look at the flows, they don't look any different. They look exactly the same. But now look what happens to my system.
Yeah, I mean, you start and you will not.
Notice what happens. Suppose, remember before, if I started at u equals 0,
Then you shoot on the
0.5, v positive, before it would hit it would bump into that fixed point, right? Now, no matter what value of v I start with, I go underneath that fixed point, go around, and go around in that cycle. And so now I have oscillations. And this is classically what happens in neurons, what's called depolarization. If I pull the electrical potential of the neuron down just a little bit, it goes from firing a single spike when you hit it to continuously oscillating, to bursting. And so this means that very small modulations of the behavior of the membrane of the neuron can lead me from a system where the neuron sits and doesn't do anything until it's perturbed, where it can fire a potential or not, to a situation where it spikes continually. And so this is the simplest possible ODE pair that can give you what happens in a neuron. The actual equations that obtaining the neuron are a little bit more complicated than this, but basically this is what you got. And so this is a system that's pretty interesting. Has anybody been able to get this the phase diagram to work? You got it, William? Do you want to show it to us? But well, before we break.
Yeah, sure. You see it?
Yeah. So that's the one for C equal to 0.1, right?
Yeah, yeah. You want me to go back and
Why don't you
change
turn
it?
C equal to 0 and see what you get? Yeah. So even this tiny change, making C positive, changes you from a pulsatile system to an oscillating system. So, okay. Well, we ran over by a little bit, but I hope that was interesting. Pedro, did you have a question?
Yes. So in that last example,
Yes.
in the fixed point, the Null-Cline was crossing going up. Was that the analysis you're doing?
Yeah, and that's wrong. You actually have to look a little more carefully to get
Oh,
that.
okay. Yeah, okay.
I was trying to explain why being on the left-hand side or the right-hand side of the minimum was important. And it's not that complicated, but I'd have to do a little bit of math to make that work. I was trying to think if I could do it without any math, and I can't.
I have as well a question. When they first showed this, I mean, at one point, I guess there was a publication who linked the mathematical model to neurons.
Yes.
From which side they came? From the math side, knowing that this exists and try to map it to the neuron, or were they first having the neural network somehow and then figured out how the attractor were looking?
Well, these
You
are
know,
not neural networks. These are single neurons. These are action potentials in single neurons. Neural networks, as defined by computation,
yeah.
don't have,
I didn't
don't-
say, so I was not saying network because we usually, because I study a network, but of course it's just two or in y and with y and x or v and u. But yeah, my question is, did they come from the mathematical side, or did they had biology that they described and then figured out Uri and then figured out that this shows this? I don't know if my question is understandable. I try to understand if they come from just observing the biology and in the end up with the math, or if they came from the mathematical side and try to map it to the biology.
Who are they?
The first person who figured out that this have to do with neurons, the first that they published this. I mean, this. What is the name? Hugo.
So
The equations name. I guess they had some. These were the ones who figured out the equations and somehow mapped it. Fits Hugo. Yeah.
So I don't remember the details of the derivation of Fitsu-Nagumo. I do know the basic history of what happened. The basic history of what happened was that there were observations in the giant squid axon, experimental observations in the giant squid axon, where they could measure the electrical potential in detail, and they could stimulate the electrical potential in detail.
Was this frog experiment?
No,
not
in frogs.
Not in frogs. Okay.
Squid. And squid. And in that experiment, they were able to determine the behavior of the electrical potential in a lot of detail. This goes back a long ways. It's early. And that led to a rather detailed model of the firing of action potentials, which is known as the Hodgkin-Huxley equations. And the Hodgkin-Huxley equations have all the properties of what we're looking at here. And they model explicitly the movement of ions across the membrane. And they model explicitly the opening and closing of what are called ion channels in the membrane. And those equations are reasonably complex. They're not so complex that we can't teach them in a class. In mathematical biology class, you often will do Hodgkin-Huxley. But they have quite a few equations and there are quite a few currents. And so Fitsu and Nagumo asked the question, what is the simplest set of mathematics that would keep the core behavior of the Hodgkin-Huxley equations, which are that cubic inflection point and that crossing? And so the original Fitsu-Nagumo equations were based carefully on experimental measurement. Sorry, the original Hodgkin-Huxley equations were based carefully on experimental measurement and were done closely in conjunction with experiment. The Fitsu-Nagumo equations were a mathematician's attempt to reproduce the behavior of the Hodgkin-Huxley equations with much simpler mathematics. So that's why I asked who was doing it, because the
Yeah,
initial work was done starting with experiment, going to a set of equations that were very tightly connected to experiment. And then there was a question of, could we do a simplification, a mathematical simplification that kept the core behavior of the complex equations, but was easier to manipulate? And that was Fitsu-Nagumo.
yeah, I was just interested in the story, and this answered it totally. So, and it's super cool. Yeah, I mean the whole equation.
It's
Yeah.
but it's very beautiful in the sense that these cubic Null-Clines wind up being very powerful. They have a lot of very interesting properties in terms of excitable media and bistability, excitability. And so if you talk to a real expert in this field like Bart Ehrmantraut, and you'll say, gee, I want a model of the immune system where either the virus can run away and you die with insufficient immune response. The virus excites the immune response kicks in, gets rid of the virus, and then disappears. The virus excites the immune response is too much, and the overactive immune response kills the patient. Or the virus comes in, excites the immune response is partial and never gets rid of the virus completely. Or the virus comes in, excites the immune response gets rid of the virus, but it never shuts off. You say, I want all of those options. And he'll say, well, in that case, you have to use the fifth order equation with the following Null-Clines. And he could just write down the mathematics immediately, just from asking what the fixed points in the behaviors are. Now, of course, Bart is a genius mathematically, and he's also spent 45 years of his life working with Null-Clines in this kind of equation. But the shape of these curves really does tell you what's possible. And here in this class, as an introductory class, we can't go very far with it. If you look in a textbook like Murray Mathematical Biology, he'll have a whole series of examples. Fitsu-Nagumo comes from that textbook. In which he will explore gradually more complex examples and show you what kinds of Null-Cline crossings, what kinds of shapes will give rise to particular kinds of behavior. And so you can really start from a set of qualitative observations. I want the system to be able to do these things. And then say the minimum mathematical structure that will do it is such and such. You can never say that there isn't a more complicated mathematical structure that will do the same thing. But you can say the minimal mathematical complexity that you need is such and such.
What I think is interesting when they figured out the whole equation. Should use names. The one who did the experiment on the neurons, they figured out the complex equation. And nice is that then the mathematicians were inspired to reduce it to the simplest possible part, right? So it was sometimes mathematics is done just because it's beautiful, and sometimes it comes from somewhere where that was just a nice story. I think it's very exciting.
It's a very beautiful equation, Fitsu-Nagumo. One thing that I will point out is that if I look at the shapes of these spikes that you see on the screen in the time series, the shapes of the curve where it comes down very vertically and then goes up steeply and then comes down again.
I think I don't see, you don't share.
Uh-oh. How long have I been talking without screen sharing? You really need to remind me when I'm not screen sharing.
Yeah, well, I think the lesson was over and I asked the question and everybody have to wait. I'm sorry.
Okay, well, this is pretty serious though, because I've been talking assuming you could see the screen. So if you look at this time series, you see this initial spike and then you see the spikes coming up again in the oscillations. So the fact of oscillation is something you see in real neurons. However, the shape of these curves is not right. In other words, the particular shape where it's steep in the front and then has this sort of up, slow, then steep down again, that's not how neurons fire. And so the simplification of the mathematics kept the basic oscillatory behavior very well, kept the overshoot very well, but the exact shape of the spikes is different. You have to give up something if you give up the complexity, but the core behaviors are right. All right. Anything else? I know we've run over by quite a bit of time, so I don't want to keep people longer. I hope people can give me preliminary project reports next week. You still have 2 weeks to finish, but we do need to try to get things done. And I do want people to have 2 chances of presenting. Try not to make your presentations too long, but enough that people understand what you've tried to do. Okay. Any other questions for tonight? Thank you, everybody, for working together and screen sharing and brainstorming together. William, go ahead.
For the presentation, do you want it to be similar to last year? Like, do you want us to make a slideshow, or do you want us to walk through our thing and explain?
Well, a slideshow wouldn't hurt, but
Okay.
if you're using a Jupyter notebook, you can also put almost everything into the Jupyter notebook. So
Yeah.
there may be certain things that you don't want to put in the Jupyter notebook. There may be background information, things that you need to show to explain what you did that wouldn't belong in the notebook. So those probably would go in slides. But for next week, I would concentrate on working on your notebooks. Because that's the thing that people need to work on the most. And if you don't have a full slideshow for next week, you'll get to do it again on the 11th or the 12th, whatever the date is of the final class.
Okay.
The point of this dry run is that I want people to be able to critique each other. I'll pair people up and ask each one of you to go over the other person's deck and notebook and critique it to try to help each other improve. And I can't do that if we wait till the last week, because then there's no time for the feedback. Okay, good night, everybody. Thank you very much. And I'm glad we got to work this through together. I hope it was useful to try these things out. Okay, good night.